So just a little bit quickly about data profit, where we've come from. We sort of start this journey in 2014, where we start looking at the world and applying machine learning to it. And when you've got a hammer, the world is a nail. We start throwing AI at kind of everything. And our journey into manufacturing as a business sort of starts with the CEO of Atlantis Foundries walking into my offices and saying, well, I've just had the worst scrap rate in 20 years. I need to do something a little bit differently. So that's sort of like where we get into this thing. So it's a bunch of computer scientists trundle off to Atlantis Foundries, and it's thick with dirt from the sand process. Foundries, despite being lean and so on, inherently generate a lot of dust. And so we're looking at this process, and we're like, well, we think we can do something. And we start predicting on engine blocks containing subsurface defects. So it's a very simple feed-forward predictor. And we're saying, as each block comes off the line, we're saying good, 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 bad, good, 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 bad, and they throw the bad ones away. And almost overnight, the scrap rate arriving at the customer disappears because the predictor is quite efficient and quite good. This has two problems. The first is that Daimler isn't too happy because they modulate contract value with with scrap, because it's a way for them to control the sort of chargebacks to Atlantis. But then Peter walks back into my office and says, Mike, you fixed my external scrap rate, but I've got the worst internal scrap rate in 20 years. And I think that this speaks to the sort of naive implementation of artificial intelligence versus how actually you should do it properly. And we start reorganizing the problem. We start saying, instead of just predicting, let's see if we can get ahead of the curve. Let's start saying, what do we need to do now in a business to make a change that meaningfully impacts quality downstream? So it's a kind of pivot in terms of the problem formulation, and we get up and we invent this new algorithm. It's not a feed-forward predictor. It's a new way of looking at the space. And then we've taken this algorithm to the world. We're currently working with folk from GKN, Gusswerke, Gerdau, Atlantis, Hulamin. We have the German automobile manufacturers, BMW in Roslin. We have Daimler here in South Africa, as well as in Rastatt and Sindelfingen. We have Volkswagen in Germany. I forget the town's name. We have next year in the States, Maxion Wheels in Johannesburg, Brazil, and Koningswinter. We have the mineral processing plants here in South Africa, MMC and Sibanye. And we have a food processing group, Oceana, down on the Western Cape Coast, as well as an OEM manufacturer called Diesel, who produce foundry equipment. And what's so exciting is that these are so many different processes. Casting a foundry is different to rolling billets of iron, which is Gerdau's problem, and is different to processing sort of mackerel caught off the coast, which is Oceana's game. But it's the same fundamental algorithm that's driving all of this. And so at some macro level, there seems to be a common way or an abstract way of presenting this. And so it's my objective in this talk to sort of present that abstract way and to sort of imbue a sense of what you need to do to your organization to get and actually apply this. And it's actually quite easy. There are just 4 or 5 things that we need to unpack. But in the context of this, we mustn't forget people. And this is one of the things that I'm really proud about Data Profit, is that we are deliberately human in the loop in this regard. It's not about eliminating people, but it's about providing insights that make people better. And I think that this way of looking at it is the correct way, because it's too easy to sort of say, right, I'm going to take an AI system that's going to run my whole plant, I'm going to get rid of everybody. And it kind of doesn't address that really dirty, difficult question. And I think that this is a neat way of engaging with it directly and actually speaking to it. So the OECD went out and did a skills survey in terms of problem solving using ICT equipment. And not shown is the bottom level, which are the number of folk who are illiterate, functionally illiterate, right through to the small gray bar on the right-hand side, which is find an email sent last Tuesday and get the sum of the numbers inside that email. And that task is interesting because you've got to take a problem, search for some data, take that data out of one application, move it into another one, so it's context switching in one's mind, do some math, some transform upon those numbers, and then put it back into the email and send the reply. And it is scary how few people, in terms of fractions of populations worldwide, are actually able to solve that task. So this bar sums up to 100. South Africa is benchmarked very close to Turkey, so it's not a great story. with folk like New Zealand actually dominating that space, with only 18.4% of their population able to solve that task. That task that you and I do 10 times a day. 1 in 5 folk in New Zealand can get that right. And they're the best out of the OECD members. It's a fascinating position, right? So when we create these systems, we're not creating it for that upper 20%. We're making it for the bottom 50%. And that's critical. And so not only is it about putting an AI system in play, but it's about communicating those results to folk who can use them at the correct level. And there's this great intellectual, his name's Edward Tufte, and he has this moniker about information at the point of consumption. It's that very simple work instruction at the very moment you need it. And then you can forget about it. No memory required, and it's providing that information to folks so that they can make the right decision without burdening them with the context switching and without the sort of necessary memory required to get it right from a complex work instruction. Building on that, PwC in 2011 published this technology forecast, and they took this view on businesses as a sort of journey to sustainability. And this is their framework, and they provide these 4 levels of companies through to maturity. So we have folk who are operating in the compliance space, and for them it's all about reducing compliance risk. And typically when we think about that, this is where the regulators in South Africa play. So it's like the rail safety regulator to make sure that folk like Transnet behave on the rail. So it's a regulated industry, and it's about managing that compliance to a minimum set of rules. Stay in your swim lane, so to speak. Then we have businesses that have an obligation. They have some license to operate. They're reducing their reputation risk, and they're inherently working up against the regulator. So typically folk like Transnet and Eskom, where it's all about they've given some license, they're in a monopoly, they have exclusivity, and they've just got to do it, and everyone hates them because they don't do it well enough in terms of some public expectation. So we think about that. Then we can think about where our listed companies fit in, and for them it's about efficiency. So it's about taking what you did today and doing it a little bit better and reducing the sort of cost of doing business. And so these operational cost savings, the value cost savings, are really what drives the growth and value of the business. It's not quite value creation, but it is some value growth because you're getting a little bit better. And then you have the sort of startup scene where you're creating a new idea, bringing that to market, and actually just giving birth to brand new value into a sort of economy. And so in terms of a forward-looking approach into this framework, you're the most sustainable when you're coming up with new ideas because you're sort of ahead of that disruption curve, as it were. So I took this framework and I thought, okay, it's really good, but I think that there's another story that's got to be told here. And that is that how is data used to drive these businesses? What are the measurements, the pulses that you're taking on your business, and how are you using that data to achieve these things? So I've added these sort of like data pairings on the sustainability maturity path. So when you're operating in the compliance space, you're using your data for control. You have some system, be it like SAP or Oracle or whatever, and here you're implementing gate functions. Every digital process is there to prevent deviation from an accepted limit. So you can look at sort of spend at a department level. You can look at HR hours, sick leave, or so on. You just keep everybody trucking along in their lane. So it's very much at the control. When you've got that license to operate and you're trying to reduce your reputational risk, you're living your life through dashboards. You've got these sort of business metrics, you're producing a graph, and hopefully the general trend is upwards. But here you've got these visual devices that are used to create some sense of progress. And the challenge here is that you've got 2 people looking at the same graph coming up with 2 different interpretations, because the data is never that clean. And so you have to have the right intuition and the right hypotheses that the data then confirms. When you're thinking about efficiencies, you're now using your data to drive your processes. You've placed an order for this, and that ripples upstream where you're placing sort of orders on commodities or on sub-assembly components. It's to some degree the system generates its own inputs, and folks' involvement with these systems are there just to monitor that nothing's sort of going out of whack, that you don't have a bug and things are failing. And when I think about innovation, we're tied with intelligent systems where you're now generating its own inputs, and we have these autonomous adaptations to the state of play. We have these things, we call them generative models, and they're really amazing at coming up with new configurations of things. And so in this space, we're sort of driven by machine learning. Your data is used to learn knowledge about the system, and then you can generate from that knowledge a new state. So that's how I sort of see the pairing of data to these different levels of maturity of businesses. The other thing I find is that around or within a company, you've got some departments that are operating in one space and other departments that are operating in another space. And I don't think it's necessary to move an entire company through to one space and keep them in a single sort of box, as it were, but to recognize that you've got these different states of maturity, and that's this sort of global rising tide that moves an entire business forward. As a side note, when we think about businesses and various business functions operating at these different levels of maturity, you can have these AI systems doing exactly the same thing. And we find that folk are selling classic ICT stuff that would have been sold in the 90s as, this is your information technology solution. Now that folk have just added AI in front. So it's your AI IT solution. And it's not true. And so we sort of find it necessary to say, well, hang on a second, we've actually got these different levels of maturity in this space. So we have platforms that aggregate data. The big pitch here is, have you seen your data lake, right? Or your data warehouse. That's really what's going on in that space. You've got these visualization systems like Tableau or ClickView or Power BI, right? Where you're taking the data that's in that lower layer and you're aggregating it into some sort of representation of the business. We have some analytics platform. To some degree, there may be an aspect of AI. If there is machine learning, it's maybe some naive kind of clustering. But it's ultimately just to automate the testing of a hypothesis. I believe in A or B. Which way does the data suggest the reality lies? Then we go up to the domain of expert systems, where you're able to provide corrections based on some knowledge on the system. And then you have this sort of holy grail where you've closed the loop and the system starts self-correcting and generating its own inputs and so on. So we must make that distinction that in some folk, we're actually just reselling ICT infrastructure. In other domains, you're actually generating new knowledge. And I think that we can also have a look at production systems globally and put them on the spectrum. And so we come up with this very simple way of separating it. We think about a degree of automation, how much human input is required to get the value out, and how wide the impact is across the production line. And you can sort of, and there's some fantastic debate around this, but for example, root cause analysis is quite a manual process. Although there are tools that can automate it to some degree, they're just driving the process. You've still got to go out there and collect the correct data, and you've got to come up with the correct sort of hypothesis that describes the core or the failure mode that you're experiencing. And you can get quite smart with things like predictive maintenance. These solutions have sort of been around since the late 90s. Doble, the UK engineering firm, actually is really good at this. And now you're giving predictions on how much available lifetime is left in a piece of equipment. So on your factory floor, you have critical machine X, and it's predicting that the rollers in machine X fails in 180 hours, or 100 hours because you've just suddenly run it a bit harder, or 80 hours left because you've just been going, or maybe 20 hours suddenly because there was an excessive vibration coming from another component. And so now what you're transitioning away from the sort of preventative maintenance regime where you would replace it on some known schedule, you're just getting a little bit more life out of that piece of equipment at so on. So the huge shift in maintenance came from the change from reactive to preventative, and it's an incremental improvement from preventative to predictive. So Gartner comes up with this hype cycle where they try and describe how technology matures and how markets react to the maturing of that technology. It starts off with some innovation trigger where you have some smart guy sitting in a laboratory somewhere. He comes up with this great idea. Eventually bubbles up. The marketing department gets hold of it and goes and tells the world about every problem that it can solve, including the ones that it can't. And the public gets excited, and the marketing department gets even more excited, and you've got this sort of like feedback loop, and everyone's raging about it. And then folk start delivering, and it's missing some expectations. So we enter this sort of trough of disillusionment, where the engineers on the line say, well, you said it would do this, and the guy's like, well, it can't do this, and the marketing guys are like, oh, it can't? So it's this interesting excitement, yeah. And then the engineers were like, well, maybe I can try this one thing, and they sort of gradually improve the quality of the no, it's okay. I think we might need it, so just keep it around, please. And then they start improving the product, and this is sort of referred to as the slope of enlightenment. And eventually you reach this plateau of productivity. And depending on the realities of the technology, you can move through this cycle at different times. So in the yellow triangles are the sort of like moonshots, and it's going to take about 10 years to reach the plateau of productivity. Whereas the sort of gray dots, which you don't see any, will be less than 2 years to reach the plateau of productivity. And there's a whole bunch of really cool little hype words that appear on this. So for example, deep learning, which is all the rage at the moment, is right up at the top of the peak of inflated expectations, right next to machine learning. And we have autonomous vehicles headed over that, but I think that the level of autonomy there is interesting because it's level 1 or level 4. It's up for debate. We have these sort of cognitive expert advisors, which are, interestingly enough, Gartner believes are entering the sort of trough of disillusionment, where you say, we can advise you to make these decisions better. And there was one other interesting one, which is the sort of augmented reality that is sort of becoming quite real now. So I think we sort of understand exactly what the value proposition of AR and VR is, and folk are sort of adopting this into lines, and it's a way more mature technology than some of the deep learning stuff that's coming out. So I want to take a moment now to talk a little bit about the experts in our business, because these are the guys who really understand what's going on. And they're not there by accident. I have this view about how an expert happens. Starts off with about 15% knowledge. These are the guys who through some fantastically privileged circumstances, end up going to great universities and getting really good educations. And then they get lucky. They end up in the right place, in the right job for them. They have a great mentor. They have a good opportunity to sort of try and innovate. And then they've got to stick it out. And the rest of a good expert in your business is his experience. He's seen it all before. She's seen it all before. There's this failure mode. Oh yeah, don't worry. You've got to go and make this little change to go and correct it. I saw this back in the 90s. And this speaks to the folk when you walk your production lines and you see these silver foxes. These are the guys who know what's going on. They know all the tricks. They know where the stuff's hidden away, and they don't want to change. And they don't want to write it down because it's not great for job security. And the other thing is that they don't really know what to do when they've seen this new mode. They have a method that they will revert to. They have sort of some process that they can go and apply to sort of get to the truth. But if they haven't seen something before, they're as good as a grad out of varsity, because the body of experience isn't there to support it. But these experts are fantastic, because what do, right? You've got, and this is very foundry specific, there's a defect type known as a subsurface shrinkage. So what happens is as the metal cools, it shrinks, and you get these voids that appear. And if a void appears too close to a machine surface, you scrap the whole component that you've cast. And if you've got these sort of shrinkage defects, and you go back and look at your pouring rate, and the pouring rate happens to be too slow, then you know, okay, great, I've got to go and change the pressure in my pressure pour furnace. And if it's too high, then I'll have to go and reduce the pressure in the pressure pour furnace. And so that's sort of what an expert does. And so folk tried in the sort of late 90s to go and sit experts down and write it all down. There's some guys like Columbus Steel who have these systems, and very few experts. And they sort of have managed to codify the set of rules when it comes to machining or casting stainless steel components. They figure that out. But as long as you've observed it and you know X and Y and Z and what the changes should be, and they've got that pretty well mapped out, then a system like this works. But we've got some constraints on it. So when we think about this really exciting platform now, right? We have people, we have all of this great technology, and we have some rare experts. And now you've got some guy who says, right, I've got AI for your business. And these are the promises he's making. It's going to be superhuman. It's going to be a lot better than your experts. And so the managing director is like, yeah, right, I tried this and it all went pear-shaped, and poor expert had to work 2 weekends in a row to get it right again. I'm not changing anything. And the response there is that your expert is actually found in the data. So you've been running your production system. Your expert's been making these corrective tweaks, these small changes. And in fact, his knowledge is codified in the process data that you've been recording. And it can be applied anywhere. And I think just to reflect on this sort of algorithm that we've come up with that's applicable across these wide range of industries, which is really exciting. So I think that there are some promises, and there's some things that we've got to keep quite real. So this is the good stuff. There are these 5 things that I want to talk to you about. And you can quite literally go back to your business and you can go and measure yourself against these yardsticks, and you can figure out how close you are to this. Sorry, was there a question? No. Cool. So the first one is this question I get every single time: how much data is required? And I want to talk about the simplest case, which was very exciting, which was stud welding in a process. So you've got some weld current. This is the amount of energy you're putting into the tips. You've got the duration, the lift height that it's moving the stud once it's applied the energy. And you repeat this at various stations. So you're going to do multiple welds, and then you'll have some quality data. You're going to have some quality data at the end of the process. So you stud weld 1 and 2, stud weld say 3 and 4 over there, and you've got these vehicles coming through the line. It's not a lot of things that you can go and change, right? So one would think that classic engineering techniques would have led to the optimization of this process many years ago. And all we needed to do to get this right were 1,500 observations. So it's almost 3 days worth of production on their welding and on the quality of those weld spots. We came up with these, into the same underlying algorithm, we were coming up with these sort of parameter combinations that would lead to improvement for every single weld. We treated each weld individually. We'd say, right, for this weld, these are the parameters. For that weld, these are the parameters. Go and apply it. And there's halved the defect rate in the stud welding process. Problem with a stud weld is that it can also pass inspection, and you end up with the vehicle way down the line, and now you're bolting on some sub-assembly component, and the stud weld breaks off. You've got to take the vehicle off the line, and it's chaos, right? To go and repair a stud weld. So as few as 3 control parameters and as few as 1,500 observations was sufficient to train this model to become an expert on stud welding. And I think that as a rough rule of thumb, for every degree of freedom or every degree so on, you need about 500 observations. And I had a fascinating conversation with the head of Industry 4.0 for Daimler after we delivered this, and he's like, "What's going on? I've sponsored PhDs in in stud welding. You know nothing about welding. How is it that you could go and halve my defect rate?" And I was like, well, in fact, I just actually used all the knowledge from your PhDs. They just didn't know that they were giving it to me. So the bottom takeaway here, big data isn't required to make AI work in your business. Then we have these really complex processes. So this, in fact, is the process flow diagram for a really interesting protein extraction method with some highly variable input source. And you get these big vessels arriving. They're offloaded. You've got some, who knows what you've caught, right? You've got some variation in quality. And depending on what's currently under production, what the sort of availability of various machines is, you're going to run the material through this line in different ways. So you can bring things in from an oil tank, or you can bring it in from some final storage through to a water tank, then through a waste heat evaporator through to bagging, or it can just do a pass-through from cookers through to hillers, dryers, and then bagging. And every combination thereof has been done. And so the question is, how do you, as an operations management expert, go to your IT team and say, I need audit data that's structured, that represents everything? And I think that isn't necessarily correct. That you can model the process, and there's some fantastic techniques to actually learn the flow of a specific material through a process, and come out with this thing that we call the unified view. And the unified view is this really interesting data structure. So you've got these processes, could be any one, can be any combination thereof, and you have some batch of material that flows through it. And at some later stage, you have another batch of material that flows through it. And what you need to construct is this holistic view upon what the parameters were for a single batch. And so you don't need to structure your data highly in order to extract this value, because you can map the process in a post hoc fashion and then reconstruct the unified view from your process recordings. So as long as you're recording the data and you're hanging on to it, you're golden. The other work, they're fantastic machine learning approaches that allow us to sort of pivot and unpack that. Then the third thing, and the IoT guys love this, is you've got to be in control. You've got to know what's happening right now. But it's really interesting because that forces you into a reactive paradigm. And here you become highly dependent on the latency of your measurements. So I'm measuring some, say, boiler temperature, and it's a real-time measurement, and I've got to keep it between these limits, and you're watching this thing, and you're making some adjustment to your boiler. And you are purely reactive. It's always in response to some sort of external change in your system. And you've just got to invest more and more and more money into making your measurement quicker. And you've got to get ahead of that curve. So you've got to change from this reactive paradigm through to a prescriptive paradigm where you can make a change in anticipation of a future state. We're really good at getting that right. The math has been there for quite some time. You can think of it as some conditional set of probabilities. Given this, I expect to be here. And we can get these models super accurate on that space. So you shift from this, I need to put in a very expensive infrastructure to make my measurements on my plant precisely, to one which says, it doesn't actually matter. I can use the information from an hour ago to tell you where you will be in 6 hours' time, so make these changes to be in the right place. We like to refer to this as, real time's actually too slow. You've got to be ahead of real time. The one point that's really an interesting point of reflection for me is quality data. And we find a variety of quality management systems out in the world, but invariably it's handwritten. And I think that at some fundamental level it's written down because it's hard to change things once it's written on paper, and it makes auditors happy. That's my guess. But you've really got to, if there's an investment to make today, it's about recording quality failures a little bit more precisely. If you can just take some granular, maybe some, if it's at a batch level, and you can think about how you record these sort of observations of failures, be it an occurrence rate down to a more specific description of the type of failure. And I always use the epidemiological analogy here. So you've got Ebola that's breaking out, and folk are coming to you with bleeding gums. And you're using the symptoms to diagnose this root cause, and you've got to try and contain it as quickly as possible. Now, it's really easy if you have some fantastic infrastructure and your guys are arriving at hospital as they're getting infected, and you can make the diagnosis efficiently. But you can't, right? Because these folk are distributed deep into the bush. It's hard to get to, and you're often learning about the Ebola infection from reported death rates that are suddenly climbing. And so you've got to make these sort of diagnoses based on second or third order information, which is invariably corrupted. So here, when you're making your record of failure, you're just going to try and focus on improving that. Be it a better description of what you've observed, or be it a slightly improved resolution in terms of time production or so on. And then I always get asked this question, how do I know if I'm making the right set of measurements? And there's a really good and simple way to look at this. So what I'm actually showing here is a quality measurement of a super complicated process. There are about 6,500 degrees of freedom here. And the color of each dot represents the result in terms of some purity of a material produced. So each point here perfectly encodes all of those 6,500 degrees of freedom. So from each point I can reconstruct what the plant state was, and I'm coloring the point based on the impurities present in the final product. And we've got this distribution now over the surface of the manifold that we've learned. The manifold encodes all my knowledge. And when my delivery team see graphs like this, they get all warm and fuzzy because there's some separation of quality. So you can see here's a bad region, and there's a good region, and there's another really good region, and here's a bad region, and here's this sort of like indeterminate, poor region. It's neither good nor bad. It's kind of like middling around. It's not great. And we're able to very directly go and say, to improve this understanding of what was going on in your plant, because it's failed to separate, you now need to go and add sensors here, here, and here. So we can connect the lack of information that's being described right through to a single point in that process. Go and add a sensor here, and you need to measure this, which is really cool, because when you go and invest in your plant, you can now go and give your engineering team direction. Hey, listen, don't you think you should actually look at this part of the process, because 40% of your defects originate here, and we can't really describe why. Right, so just to sort of close the loop, we don't need these huge amounts of data for these AI systems. Typically, thousands of rows is sufficient, and tens of process parameters are required. So you don't need to have this very modern plant. Chances are, if you're controlling it, you're measuring it with sufficient resolution for systems like this to have impact. You've got to have some aspect of traceability, but again, we can infer this through some fantastic machine learning models. You don't need this thing to be real-time at all, because we get ahead of that real-time curve. Got to improve your quality measurement. It really unlocks all of the value hidden in those process measurements you've made previously, and we can sort of guide you on where you put more sensors at a later stage. So now on the really, really cool and exciting things, this is Atlantis Foundries before I get involved. So each red cross is the full description of production of this huge gray iron engine block, a half-ton engine block, for all of the process parameters that led to its birth, described and compressed into this single set of two coordinates, x and y. The blue marks are the historical production regimes. So we go back and look through 2 years of production data, and we say, where did the plant operate on frequently? So every time a single point goes down, we sort of record a density at that place. We look at this accumulated density over 2 years, and so we find that we have these production regions in these various spaces here. And this is the discovery of the plant paradigms. So for example, it wasn't in this case, but by example, in winter, when you're not adding as much water to your return sand, you may operate in that space, and in summer, when you have to add more water to your return sand, you're operating in that space. And this is a really interesting time series plot, because we were just moving through the year. And you notice the scatter shot in the bottom left-hand corner of this plot. And what's happening here is you've got this huge factory, and everyone is doing their job right. You've got this sand guy who's looking at his sand process, and he's keeping his bentonite additions between the limits that were given to him by his line manager. Right, so he's got to keep it between 4 kilos and 10 kilos, and he keeps it spot on in the middle. And you go right down to the metallurgist, who has to keep the amount of selenium that he's adding between some amount and some amount. And everyone is doing their job right. But what happens is the process at the bentonite additions drift to one end of the control, the controlled tolerance band. And you're sitting there, and it's close, it's in, he's not doing anything wrong. And you've got the selenium amount that's also adding up a little bit too high. And so you've got this tolerance stack up. But because it's communication in this space is not possible, no one's able to run the compensatory correction. And so you end up producing engine blocks where everything's gone right, but you've produced scrap. So in other words, your root cause analysis isn't going to tell you anything. But they end up as this sort of scattershot here. And the presence of points down here corresponds to increased scrap and rework rates that are measured at the quality station. So the key objective is to control this loop, to make these compensatory corrections without having to have guys get around and have a chat every 2 minutes to make these changes. And so that's exactly what we do. So we find we've identified this plant operating paradigm where the machines are inherently capable, and we give them guidance on the small set of changes that they've got to make once a week to get there. We give these guys a list of 20 things to do, and typically in a week they solve 5 of them, which is fine, because you've got another week, and you've got another week, and another week. And every week I'm going to rank in order of most important to least important the 20 things you've got to go and knock off your list. And so these engineers scurry away into the foundry, and they go chat to this guy. You've got to go and focus on this week, and you've got to go and look and focus on that next week. And they make these changes. They end up in this stable operating regime. The first thing that happens is that the variance in scrap and rework goes right down. And I'm chatting to the CEO. He's like, yeah, it's nice that you solved my scrap problem, but damn, I'm sleeping so much better because I'm not waking up tomorrow with a scrap crisis or a rework crisis. And of course, because it's continually optimizing, we eventually drive them to 0% scrap in the context of a global benchmark average of 5 to 6%. They go on to become Daimler's best supplier of large gray iron, I think it's Class B engine blocks. This is the stud welding, and these are the results. And this is now across different stud IDs. This is the system operating without my input. Here we're looking at 6 process parameters. There are an additional 3 that we look at relating to the setting time, how long the robot must wait for the surface material to settle. And across the board, we make an improvement with an overall reduction of 55% of stud welding failures. So thank you very much. Appreciate your time.